The James Webb Space Telescope, JWST, has once again shaken the foundations of our understanding of the universe. What if the farthest reaches of the cosmos are even more ancient and mysterious than we ever imagined? Recent discoveries by JWST suggest just that, revealing galaxies and star clusters from the dawn of time, challenging everything we thought we knew about the cosmos. Imagine peering back in time to the infancy of the universe, where the first stars and galaxies began to light up the darkness. The JWST has done just that, unveiling secrets that could revolutionize our understanding of cosmic history. JWST has reached the farthest point in the observable universe and shows us structures that are almost impossible to see with previous technologies. Using the gravitational lensing effect, the telescope detected 5 ultradense protoglobular clusters in the cosmic jewel arc galaxy that existed only 460 million years after the Big Bang. Even more amazing is JADE's discovery of a galaxy called JWST, which existed only 290 million years after the Big Bang, making it the oldest galaxy ever observed. This extraordinarily bright galaxy suggests that it has a mass several hundred million times that of the Sun, which raises deep questions about how such large and bright structures could form so quickly after the Big Bang. Einstein's general relativity explains that gravity is the result of the curved spacetime effect of matter and energy. This curved spacetime determines the paths that energy and matter follow, allowing light that normally travels in a straight line to be bent and amplified by massive objects, a phenomenon known as gravitational lensing. JWST used this effect to observe the cosmic pearls of the Arc galaxy, whose light would otherwise have been too faint to detect. Previous Hubble images of this galaxy were too dim, but JWST's NIRCam and spectrometer provided a detailed study, revealing a clear low-luminosity galaxy and structure that can help us understand early star formation. The discovery of protoglobular clusters by JADE's JWST provides a unique window into the early universe. These clusters, which formed approximately 290 million years after the Big Bang, are the precursors of today's globular clusters and provide insight into the conditions and processes of star formation during that era. By studying these clusters, scientists hope to understand the distribution of dark matter in early galaxies and gain clues about the plan of the universe. Additionally, the JWST observations challenge our understanding of cosmic reionization, the period when the universe transitioned from a neutral hydrogen-dominated opaque state to a transparent, luminous state. This process began with the formation of the first stars, known as population 3 stars, which were massive and short-lived. They produced the ultraviolet light necessary to ionize hydrogen, marking the cosmic dawn of the universe. The existence of ancient galaxies like JADE's JWST, which appear only hundreds of millions of years after the Big Bang, suggests that stars and galaxies formed faster and differently than previously thought, or that the universe may be much older than we think. The implications of an infinite universe extend beyond theoretical physics into the philosophical and existential realms, challenging our current understanding of cosmology based on the finite size and age of the observable universe, which is approximately 13.8 billion years. JWST continues to push the boundaries of our knowledge, providing unprecedented views of distant galaxies, star-forming regions, and gravitational phenomena. By studying space, astronomers face fundamental questions about the nature of dark matter, the origin of galaxies, and the structure of spacetime, bringing us closer to a comprehensive theory of cosmology that encompasses the extent of the universe and our place in it. The universe as we understand it today began with the Big Bang about 13.8 billion years ago. This explosive event set the stage for the creation of matter, stars, and eventually galaxies. For decades, astronomers have peered into the depths of space, trying to piece together the history of space.
The advent of telescopes like Hubble brought us tantalizing glimpses of distant galaxies, but the James Webb Space Telescope truly changed our view of the universe. JWST's ability to observe infrared radiation allows it to see through the cosmic dust that obscures many celestial bodies from optical telescopes. This feature opened new windows into the early universe, allowing scientists to study the formation and evolution of the first galaxies and stars. One of the most important discoveries of JWST is the observation of 5 ultradense protoglobular clusters in the cosmic Jewel Arc galaxy, located approximately 460 million years after the Big Bang. These clusters provide an unparalleled picture of the earliest stages of star formation and provide insight into the conditions and processes that drove the formation of the first stars, JWST, a galaxy that existed only 290 million years after the Big Bang, is another pioneering achievement. This galaxy is the most distant point in the observable universe and the oldest galaxy ever observed. Its extraordinary luminosity, which suggests it is several hundred million times the mass of the Sun, presents a significant challenge to our understanding of how the universe could form such massive and luminous structures so quickly after the Big Bang. This discovery raises profound questions about the nature of the early universe and the processes that led to the rapid formation of stars and galaxies. Einstein's theory of general relativity played an important role in understanding the universe. According to this theory, gravity is the result of the curvature of space-time due to the presence of matter and energy. This curvature affects the paths of light and matter, leading to phenomena such as gravitational lensing. JWST used gravitational lensing to detect distant objects that would otherwise be too dim or too far away to see. This technique involves light being bent and amplified by the gravitational field of massive objects such as galaxy clusters, allowing astronomers to study the most distant and oldest structures in the universe. The cosmic Jewel Arc galaxy detected by gravitational lensing offers a unique opportunity to study the early universe. Without the lensing effect, the light from this galaxy would have been too faint to detect with current technology. The Hubble Space Telescope previously took faint images of this galaxy, but JWST's advanced instruments revealed it in more detail. JWST's infrared spectrometer confirmed that the scattered light from the cosmic Jewel Arc cactus is indeed a separate galaxy that appears to be small and faintly bright. Further analysis will reveal more about the structure, star formation processes, and elemental composition of this early galaxy. JWST study of protoglobular clusters is particularly important. These clusters are considered to be the forerunners of today's globular clusters of hundreds of thousands of stars. By observing these early star clusters, scientists hope to gain valuable information about the conditions and processes of star formation in the early universe. JWST's high-precision observations and spectroscopic studies of these protoglobular clusters provide new information about their properties, including composition and evolution. This research could help scientists understand how the first structures of the universe formed and how matter evolved over time. In addition to studying the formation of the first stars and galaxies, JWST observations also shed light on the reionization epoch. This period, which occurred approximately 300 to 1 billion years after the Big Bang, marked the transition of the universe from an opaque state dominated by neutral hydrogen to a transparent state filled with ionized hydrogen. The formation of the first stars, known as population 3 stars, played a crucial role in this process. These massive, short-lived stars produced large amounts of ultraviolet light that ionized the surrounding hydrogen and ushered in the cosmic dawn. The existence of ancient galaxies such as JWST, which formed only a few hundred million years after the Big Bang, suggests that the processes of forming stars and galaxies happened faster and differently than previously thought. This challenges our current cosmological models and raises the possibility that the universe may be much older than we expect. Studying these early galaxies provides important insights into the conditions that prevailed during reionization and helps scientists build a more comprehensive timeline of cosmic evolution. The implications of an infinite universe are profound and extend beyond theoretical physics into philosophical and existential dimensions. If the universe is indeed infinite, this suggests that what we observe is only a fraction of a much larger cosmos. This idea challenges our current understanding of cosmology, which is based on the finite size and age of the observable universe of about 13.8 billion years. JWST continues to push the boundaries of our knowledge, providing unprecedented views of distant galaxies, star-forming regions, and gravitational phenomena. By studying space, astronomers face fundamental questions about the nature of dark matter, the origin of galaxies, and the structure of spacetime, bringing us closer to a comprehensive theory of cosmology that encompasses the extent of the universe and our place in it. Studying the early universe is not only about understanding the formation of the first stars and galaxies, but also about unraveling the mysteries of dark matter. Dark matter is thought to make up a significant portion of the mass of the universe, but it does not emit, absorb, or reflect light, making it invisible and detectable only through the gravitational effects of visible matter. JWST observations of distant galaxies and protoglobular clusters provide valuable information about the distribution and dynamics of dark matter in the early universe. By studying how dark matter affected the formation and evolution of these early structures, scientists hope to gain insight into its nature and role in cosmic history. Gravitational lensing, one of the most powerful tools in modern astronomy, has revolutionized our ability to explore space. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravitational field of a massive object, such as a galaxy cluster, bends the path of light from a distant object.